Hi everyone, it's Judy Warner. Welcome back to the OnTrack Podcast. Today I have an illustrious guest, which is my friend Steve Sandler, who's the managing director of Picotest. Steve has an amazing background doing power integrity, modeling, simulation for such massive systems as the CERN Accelerator and the International Space Station. And he's going to speak at AltiumLive this year, and I wanted to give you a little taste of what he's going to talk about in regards to simulation. So lean in, enjoy. I'll see you on the other side. Welcome to Altium's OnTrack Podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media. Well, hi, Steve. Thanks so much for joining us again. I'm glad to have you back for the second time on the podcast.
No, thanks for inviting me. It's always fun.
It's always fun to chat with you. So why don't we jump right in? I'll have you give more of your fun stories from the past with the space station and CERN and so much more towards the end of the podcast. But I wanted to right up front hear about the talk that you're going to be giving to our virtual edition of AltiumLive in October. So tell me about your title and what you're going to cover.
So I'm really excited about AltiumLive. You know, I've been doing simulation since the 1980s, so I have a bit of history with it. And I'm going to talk about the relevance and the essential need for simulation as part of the design process, but not only for design, but also for optimization and for troubleshooting. And troubleshooting is one of the bigger aspects. So you mentioned that we'll talk later about, my experience simulating the accelerator at CERN and also the International Space Station. And a lot of that is for troubleshooting things. So I'm excited to talk about that.
So have you come up with the title yet for your talk, and what can design engineers what are going to be takeaways? We're only giving you an hour on a really difficult subject. So what can they expect to take away from your talk, and let us know if you got a title.
Well, I'm still playing with the title a little bit, but for sure it's going to include the essential need for simulation. Maybe something like simulating is an essential tool. And for sure, I'll try to incorporate somehow the optimization, the design and troubleshooting, because that is kind of the trifecta. There are a couple of takeaways. And, I've been simulating for, I was going to say almost 40 years, and it scared me. But yeah, it is. It's almost 40 years now. And there's a lot of things that we learned along the way. One thing is that for simulation to be useful, it has to be fast. And people don't really recognize that, so they tend to try to simulate everything. And of course, the more you simulate, the longer it takes, the less useful it becomes. And so one of the key takeaways is that it's really important to identify what it is that you need to simulate in order to get the information that you want. If you simulate too little, you're not going to get the right answers. And if you simulate too much, it's going to take too long. And so we need to kind of get that right. When I started my company for simulation, I had one rule, and the rule was be right. A lot of the stuff that we work on is big budget stuff with big ramifications. And it's not always dollars. For the automotive industry, they do a lot of simulation. And for them, it's about recalls, it's about liabilities, and of course, squeezing out that last penny. So optimization is a big part of why they simulate in the automotive industry. The industry that I'm in is mostly military and defense, space-based things. And if those don't work right, then really bad things can happen. And then on the science side, and I work a lot on the science side too, you have things like the space station that costs $16 billion, and you launch it and it either works or it doesn't. We're really excited about the James Webb Telescope coming, and the James Webb Telescope, a lot of people don't realize this, but one of the difficulties about it is that it's not in a low Earth orbit, it's in a higher orbit. And so if something goes wrong in that launch, or if something goes wrong in the deployment, there's not a way to fix it. There aren't going to be spacewalks. It's just going to be a lost many billions of dollars. And so we use simulation to try to make sure that we got everything right because it matters.
And I've heard about the James Webb Telescope because we did a podcast with a guy that's working on the Sophia telescope, which is actually out of the side of a 747, yes, if you could believe that, right? And so he was saying with the James Webb telescope, it's one launch and done. Like, yes, exactly. As you said, it doesn't come back. You can't bring it back down in the 747 and tweak it.
Yeah. And even things like actuating the telescope, unfolding it once it's launched, there are 108 actuators in the James Webb telescope. And if only 107 of them open, we don't have a telescope. So being right really does matter. I think that's really important. Know why you're simulating what you're simulating. People tend to misunderstand why and when and how we do what we do. And it's because it's kind of a circle, right? So the designers that designed the parts, the semiconductor companies, they started out with simulations, and they simulated their part using foundry models, and hopefully they got it all right. And then they make a part, and then they measure it to characterize it, make sure it does what it's supposed to do. And then they make a simplified model for designers to use, and we assume that model's pretty good, but it's really unclear which came first, right? Are we simulating so that we can make the model? Are we measuring so we can make the simulation? It's an endless cycle, right? It's kind of a circle that just keeps evolving, and I want people to make sure that they walk away with an understanding of where it is that happens in the system. And in fact, I remember maybe around the mid-1980s, simulation was working pretty well. And the managers at the companies decided, now we don't actually need to build stuff because the simulator could do everything, and we could just do it all in the simulator. And that didn't work out so well. So they decided, well, we've got to go back to making breadboards and stuff. But if we're going to make breadboards, then we probably don't need to simulate either, right? Since we got to build it. And so I think that's another really important takeaway, is that it's two very essential tools that also have a synergy, right? They work better together than they do independently. So when we simulate and measure, we get benefits that are bigger than either. And that's actually what we're after. So that's probably one of the biggest takeaways.
So I'm hearing from a lot of you sort of gurus out there that a lot of the different things, the problems used to be more at the systems or chip level, and now so much of the problem is coming at the board level, what's happening on the PCB. As you're out doing the work that you do, Steve, what are some disconnects you're seeing that are prevalent in the marketplace in regards to board level issues?
So that's a really good point. And, I do work a lot at the system level. And in fact, even in Space Station, every report that I wrote for Space Station had a disclaimer that said it didn't include printed circuit board effects. And today I would say, don't bother, because it's all printed circuit board effect. Our high-speed tracks, right? We've gotten really good at signal integrity analysis, but probably only in the last 20 years, maybe even less than that it's truly mainstream. Power integrity is probably much younger than that. We started simulating, board level power integrity probably only 10 years ago, seriously. And of course, there are gurus like Istvan Novak that's been doing it forever, but mainstream, no, probably just the last 10 years. I often say that I wish I was a young engineer now, right? They have the coolest things. They can 3D print everything. The technology is just so much bigger and better than it was when I started. When I started on Space Station, we weren't even allowed to use microprocessors. Everything was digital logic, and most of it wasn't even printed circuit boards. It was wire wrapped. And we've come a long way. So it'd be really fun to be an engineer. But with all of those new high-tech gadgets and toys comes a whole new set of problems, right? Your little tiny cell phone has 3 different Wi-Fi transceivers in it, Wi-Fi, Bluetooth, cellular. Everything is so close together that everything impacts everything. And so, a good friend of mine, Ken Wyatt, the EMI guru, he says, you have to start all the way with what is the board stack up, because so much of EMI is dictated by whether or not you got the right stack up. I just did some simulations for Europa. That's the first satellite project that I'm aware of that's using gallium nitride. And one of the things I was really afraid of was ground bounce in the printed circuit boards. And we did the board level simulations, and holy cow. Yes, I was right to be worried about things like ground bounce. The higher the frequencies go, and we're at 100 gigahertz now, right? At 100 gigahertz, the jitter margins are so tiny, and you push things close together, noise from the other side of the board shows up everywhere. In fact, I have a new measurement class that's starting in August or September, and one of the things that we're showing in the first class, I think it's in the first or second class, is how much noise there is just in ambient labs. I mean, what does the noise look like in my lab, and how does that get into our boards and cables and traces on boards look like antennas? And it's really incredible to see what it actually looks like up close. So I don't think you can leave out the board anymore is the point.
Yeah, I keep hearing that from y'all, that it used to be, boards were simpler. They weren't screaming at these speeds. They didn't have all these wireless features and Bluetooth and all that. There's just a lot of opportunity for a mess. So I'm excited. So for our audience, I reached out to Steve because I was talking to our very own Ben Jordan, and our internal Altium developers have advised me that in Altium Designer 21, they're really going to do a lot with our SPICE simulation tool. And so it's going to be significant. And I thought, well, it'd be really interesting to get someone that was good at SPICE simulation. And I always think of Steve as sort of a power integrity guru, although he understands other things. And so I reached out to Ben Jordan and I said, what should I do? How do I find somebody who's excellent at SPICE simulation? He goes, I have a few good books that I love, love, love. Let me go tell you who the authors of those books. And I was saying, I was in a separate conversation. I was talking about Steve Sandler and power integrity. And then he comes back to me. He goes, you'll never believe who wrote my favorite SPICE simulation book. And I said, who? He says, Steve Sandler. So that's how we kind of came, landed on this topic. And we're going to share that and some of Steve's other works in the show notes. So make sure you go take a look at those. So, well, we're very excited to have you. As you know, it's going to be virtual, so it'll be a little bit of a different experience. However, we are going to give Steve some time to answer your questions and have some live engagement. So, okay. So let's go back to your previous company, AEi, and tell us a little bit about your most famous and maybe difficult project, and tell us a little bit about AEi.
Sure. So AEi was a company that started back in 1995. And as a simulation and modeling expert, there really seemed to be a lack of that capability in the space world. And at the time, Space Systems L'Oreal was really asking me to come work for them. And I didn't want to take a job, but I said, you know what? I'm going to be an independent consultant, and I started a company called AEi Systems. And while I was working there, we were all working on a space station. We just had started, and I overheard a conversation saying, "How are we going to do the worst case analysis of a space station? Right? Nobody's ever done anything so big, and how would we even model it?" And I heard it. It was just before Christmas, and I went home, and I wrote an unsolicited proposal to do the model of the entire space station and the worst case analysis. And I won. And it was kind of funny. I was living in Chandler, Arizona, and NASA and Rocketdyne and L'Oreal. they showed up and I said, so we're trusting a $16 billion space mission to a guy working out of his living room. You realize what happens if you get this wrong, right? So the pressure was really on. And I spent the next 6.5 years cranking out probably almost 300,000 pages of analysis, but we did it. We simulated the entire space station all the way from one end to the other, mostly in the power deck. That was my responsibility, was the power deck. And one of the very first simulations that I did was the space station going through a solar eclipse, which maybe not everybody knows happens about every 90 minutes at 17,500 miles an hour, which is the cruising speed of the space station. And that means that every 90 minutes we transition from being powered by solar cells to being powered by batteries. And so what does that transition look like? And I did a simulation, and that simulation showed that every time it would go through eclipse, the voltage on the master bus would dip below the reset, and every instrument on the space station would reset every 90 minutes. And of course, I got that normal pushback, SPICE models can only do so much, and garbage in, garbage out, and how do you know your models are accurate? It wasn't until about 18 months later that they actually had hardware to do the test, and they sent me a picture that looked just like what I simulated. In fact, I'll show it in the AltiumLive presentation, and it actually came with a little Post-it note that said, "Oh crap, can you fix it?" And I said, the good news is that I can, and the bad news for you is that it's going to cost a lot more than it did 18 months ago. So buckle up. And we had a lot of fun. But that it's simulations like that we need confidence in, right? This is why we're doing all of these little models. That's why we do the measurements of the models. That's why we measure all of the little details, because at some point, I tell my customers, at some point you're going to jump, right? There's not a question, you're going to jump. There are things we can't do. There are things we can't measure. And at that point, you have no choice but to trust your simulator. What do you have to base that trust on? The only thing you have to base that trust on is experience. And so we need to build up enough experience. In my case, I needed to build up enough experience that I could tell NASA and Rocketdyne and Space Systems L'Oreal that their baby was ugly and suffer the wrath and ultimately turn out to be right. So that's kind of what we're after is that.
Well, I'm excited to, again, sort of give you as a gift to the industry, because obviously most of the things that the design engineers that will attend AltiumLive are doing very important work, but a much smaller scale than things like the space station. So we really look forward to having you there. So in regards to you gave me sort of a little brief history of SPICE. Would you mind going through that with our audience?
Sure. So first, despite all his gray hair, I wasn't one of the first to simulate SPICE. SPICE was actually introduced by Dr. Larry Nagel back in 1969. And I didn't actually start simulating until 1985, which was when the company that I worked for got their very first computer. And it wasn't Dr. Nagel's first simulation package either. So I'm guessing he'd probably be shocked to find out what it is that it can do. But back then, he was mostly interested in integrated circuits. He wanted a program that could simulate integrated circuits. And along the way, it went through a couple of major upgrades. For example, when it went from SPICE 2 to SPICE 3, they added equation-based behavioral modeling. PSpice had done it themselves, somewhere between SPICE 2 and SPICE 3, so they became incompatible. SPICE 3, they had a syntax for behavioral modeling. Georgia Tech added what they called XSpice that added C code models to run faster. And of course, HSpice is probably the premier simulator today for integrated circuit development. And so along the way, it's split up into all of these different factions. And some of these factions got embedded into other software. LTSpice now has their own syntax, and each one of them has their own libraries. And I always tell people, the SPICE engine is the SPICE engine. That's open source. And so what companies lend to it is the input side, the schematic capture, like Altium does, and the post-processing, the graphics capability. When I started, we had a dot matrix printer, and all of our plots came out with the little dots. Today we got beautiful printers, so even that's kind of migrated a long way. But that's mostly what they added. What I'll tell you is that, we learned early on with SPICE, garbage in, garbage out. And so what's really important about it is the models. And most models aren't right. And so it's up to every simulator, every person doing simulation has to validate the models that they're using. Otherwise, you're just wasting your time. And another thing I would say is that, when you're looking at these simulators, people didn't really plan for SPICE to be what it is today, right? I mean, it's huge, it's everywhere. But it seems like a lot of individuals doing their own little simulations in their cubicle and solving their problem. And like you said, everything is kind of a system and everything is on one board. So I think what becomes essential going forward is that all of these little models that people are doing in their cubicles all have to attach somewhere to each other if you're going to try to accurately simulate a system. And of course, that needs to include the printed circuit boards and even things like the interconnecting cables and the ribbon cables. And we need to even model those. And so I think one of the things that is more recent isn't the evolution of the simulation engines, but the evolution of the libraries.
Interesting. Well, I think, don't anybody hold this to me, but I think one of the things we're going to do is I think we just mostly could integrate with NG SPICE, but I think we're opening that up because obviously, as you said, there's a lot of different factions of SPICE. So I think that's one of the things we're doing. You also mentioned something about WEBENCH and where that ended up. Tell us about that.
I love challenges, and that was definitely one of my bigger challenges. But I actually went back and looked at this article since we spoke about it, but it was back in 2005. National Semiconductor realized that one of the keys to selling more semiconductor components was having SPICE models for them, which was a big endeavor. And of course, not everybody owned a SPICE simulator, and they didn't really want to be in the business of making, models to give away. So they had this brainstorm. They would build a internet-based simulator, and then you could sign up. You'd have an account for National, which of course, as a marketing person, there's huge benefits in getting people to register for that. So people would register to use WEBENCH, and then they would simulate over the internet. They ran into a huge problem almost immediately. And it's one of the first things I said, and that is that for simulation to be useful, it has to be fast. And, in 2005, we didn't have 100 megabit Wi-Fi in the house. And so it wasn't quite so fast and it just wasn't working. So they came to me and said, Steve, we really want to build this WEBENCH simulator over the internet, but it's too slow. Can you fix it? And I did. And I came up with this brainstorm that, we have two kinds of models that we simulate in SPICE. One is a true time domain transient simulation, and it solves voltage and current equations at every time point, and it's really accurate and also really slow. And we also have behavioral models that run really, really fast. And so I thought, well, if I can run a behavioral model that runs really fast, and since it knows the operating conditions at every instant in time, I could just have it tell these transient switches to, all right, turn this switch on now, turn that switch off now, and not have to solve all of those voltage and current equations, not need to do all of those simulations. It was kind of event-based, right? So when we knew something would happen, then we'd simulate that. And then we would just leave it status quo in between those things. So it's kind of an overlay of two different simulation layers simultaneously, and that became WEBENCH. And that's still the way they do it. And more recently, in 2015, I think it was, I ported that to ADS to allow the incorporation of EMI simulation and harmonic balance simulation to get time domain even faster. But those are the kinds of things I think that we'll see in the future for SPICE. Is the big upgrades will be how to make it go faster. Mm-hmm. The speed is everything.
Speed is everything, and it's not that, pardon the pun, it's not slowing down, right? The speed at which
Right.
we increase the speed is, there's
And
always
engineers are spoiled, and we like to complain a lot. So they say, wow, that space station simulation took 2 days. Well, now I could do it probably in 3 hours. I said, you want to guess how long it would take to do it without the computer?
Yeah.
Right. But we take that for granted. Back in the 1960s, we did this without the simulator. It was a lot harder. Trust me.
That's crazy. Well, the last thing I wanted to talk to you about, Steve, sort of a fun thing. I used to on the podcast talk about designers after hours or gurus after hours. And I happened to see something on LinkedIn yesterday that had to do with your culinary hobby on the site. So tell us how the PI guy came the pizza guy.
So that's what I do when I'm not doing my day job. It's actually kind of an interesting story. But back when my younger daughter was a teenager, we were looking for things to bond over. And you've had teenagers. It's hard to bond with a teenager. But we found some common interest. I like eating bread. My daughter liked artisan bread. And so we decided that we would learn to make artisan breads together. And we got a great French book on making dough. And one day we just decided, you know what? I mean, we know how to make dough now. We should try to make pizza. And we did. That's probably about 15 years ago now. And it really stuck. It was like, wow, pizza's so simple. And yet so perfect, right? But so perfect. And I've spent the last 15 years trying to perfect my pizza. But it's such a paradox from my science side, right? On the engineering side, there's nothing I can't calculate or simulate. When you get to pizza dough, it does whatever it feels like. Your job is to go for the ride. So you have to kind of learn to make dough by feel. Mm-hmm. and not so much by equations. And so I kind of think it balances me out a little bit. But now I've been making pizza for about 15 years. I have an Italian pizza oven at home. And I think there's this thing that people think they made it to my inner circle when they've been here for pizza. So so every once in a while I'll post something about it. And of course, in every presentation, there's a picture of pizza somewhere.
Well, I keep saying, whenever we get out of this season of COVID, I'm storming your backyard because you guys, my mouth was watering yesterday or day before yesterday whenever you posted it, because I didn't know you made, I love sourdough bread, pizza, whatever. And you had like grown your own cultures and you're making sourdough pizza crusts. And so, well, I'll try to just share the LinkedIn link, but for our listeners, if you'd like to connect with me or Steve, you can too behold Steve's after hours talent. So, well, Steve, thank you so much. Oh, did you want to tell us a little bit about Picotest, the company that you own and run now? We forgot to talk about that a little bit.
I'll just give you a brief rundown. I retired when I sold AEi Systems. That was my plan. Finish space station. It was incredibly intense and retire. And I did until I got remarried. And then my wife went back to school and I got bored and I needed to do something. So I said, you know what? I think I'll just start another company. And so I started a company called Picotest that manufactures test accessories, mostly for high-tech companies, the Apples and Broadcoms of the world. And a lot of it is power integrity related, but I make mostly niche products that didn't exist and that I needed to make measurements for creating my models and simulations. And since I had to develop them for myself, I built a company to make those available to the rest of the world too. And Picotest is now almost 14 years old. No, 12 years old. So it's been around a while. It's doing pretty well. And I have so much fun doing what I do.
That's great. Also, you guys, if you go connect with Steve Sandler on LinkedIn, go through his activities. And he recently did a tour inside of his lab that will make y'all drool. Plus, it's the neatest lab I've ever seen in my life. And he's going, oh, this is messy. I'm like, please. I've seen most labs, and that doesn't look anything like it because he has a beautiful setup at his house, and he works with all the instrument companies. So he just has the dream of, and then he has all his Picotest probes and things in the drawer. Anyways, if you ever want to see like the dream lab, go connect with Steve Sandler and watch that. I think we reposted it too, so it's probably also on the Altium thing, on the Altium LinkedIn post. So that's really fun. Well, Steve, I always enjoy talking to you. Thank you so much for agreeing to speak at AltiumLive. I know that that our attendees are going to love learning from you and enjoy your all your wisdom. And thanks again for coming on the podcast and giving a little taste of your topic and your incredible background.
Thanks so much. And speaking of taste, you have an open invite for pizza. So
okay,
when you make it here, we'll do it.
Okay. All right. I keep hinting, but I'm not very subtle.
You're always welcome.
Thank you. To our listeners, thank you so much for joining us today. I hope you enjoyed this conversation with Steve Sandler of Picotest. AltiumLive registration is going to open in about a week, so make sure you sign up. It's free, and it's going to be virtual. So all are welcome, and we are lining up quite a program for you with people like Steve Sandler. So thanks for joining. Please remember to like, subscribe, and comment so we know what you want to learn about next time. Until then, remember to stay healthy, stay safe, and always remember to stay on track.